So this is the second lecture, and in this lecture I will start from where I left off, trying to develop a theory of plasticity of solids in terms of dislocations and a continuum theory of dislocations, and then go over to a sort of very short review of our attempts at understanding the initiation of plasticity. Because what I'm going to talk about first is about a solid which is already plastic. So it is already in that plastic regime, and it says how one can calculate deformation of a plastic solid. Okay. So as I said last time, that certain things when you look at them singly, they are sort of difficult to handle, but when the numbers are very large, things somehow become easier. So the first thing that we have to define here is the so-called dislocation density tensor. So I told you that dislocation itself is defined by two vectors. One is the tangent vector, which is a geometric thing, tells you how the dislocation segment is oriented, and the other is a Burgers vector, which tells you how it affects the surroundings. So if you have two vectors, you can construct a tensor Ti Bj, and then there are alpha dislocations. Each dislocations are at different places, r alpha. So by counting the number of dislocations with tangent vector Ti and Burgers vector Bj at the alpha-th position, you can construct a coarse-grained dislocation density tensor. So this is called the Nye dislocation density tensor. So this, of course, has to satisfy a constraint such that its divergence has to be equal to 0. And this constraint, it simply means that dislocations, they cannot suddenly end. So if you sort of draw a little picture, then you can convince yourself that dislocations either have to form a loop or they have to go to the surface. They cannot suddenly end in the bulk. Okay? And this constraint is administered by demanding that the divergence of this is 0. Okay. So now we could work with the dislocation density tensor, but it turns out that it is easier to work with another quantity, and that is known as the plastic distortion field. So how do you define the plastic distortion field? Suppose you look at the total deformation gradient. So this ui is the displacement. So you look at the total deformation. So that is the gradient of the displacement. That can be broken up into two parts. Okay? One coming from the smooth elastic part. So this is just elasticity. So this I am calling as beta ij e. And a second, which is a singular contribution, and that comes from the presence of defects and dislocations. So this is beta ij p. So beta ij p is the plastic distortion field. Okay. So how do I connect it to the dislocation density? Suppose for the moment that beta ij e is 0, then the difference in the displacement, if you go around some curve which contains some plastic distortion, will be given by this. There is this some contour integral. Okay. Now you can use Stokes' theorem to convert this contour integral into a surface integral. So there will be a curl of this beta, okay, and then integrated over some surface. Now we know that the Nye dislocation density tensor, it is a dislocation density. So if I integrate it over the surface, it should give me the total Burgers vector. So it is like a Burgers vector density. Okay. So this curl has to be equal to an integral over the surface of the Nye dislocation density tensor. So now, since this is a very general statement and appears for all possible surfaces, then the integrands themselves have to agree with each other. So which means that the curl of the plastic distortion field is the Nye dislocation density tensor. Okay, and this relation is very similar. You can have lots of electrostatic or electrodynamic analogies. So if your dislocation density tensor is the magnetic field, then this is like the vector potential. Of course, this is more complicated than electrodynamics because here there are vectors and here you have one more index. So these are tensors. Okay. The nice thing about working with the plastic distortion field instead of the dislocation density tensor is that this constraint is automatically enforced. Because this comes from a curl, its divergence is always 0. Okay. So this is the same advantage that you have working with vector potentials instead of the magnetic field. Because you don't have to separately impose the constraint that divergence of B is equal to 0. Okay. So now I am going to just state the result. So if you have some dislocation density, that has to be related to the stress, and this is related to the stress by some kernel. So this is a second order tensor, this is a second order tensor, so this has to be a fourth order tensor, rather like elastic moduli. And this calculation one can do, and I have sort of cited this thesis by Limkumnerd, and it's there on the net. So if anyone wants to go through this calculation, it's sort of straightforward but tedious. But all that it means, all that you have to do is that you know the stress distribution of a single dislocation and then convert it to a dislocation density. And that can be done in Fourier space somewhat easier. And this is the Fourier space expression for this kernel. So there are Kronecker deltas here, and there is this antisymmetric tensor here. These are the Fourier components, and the elasticity goes in these two quantities, where this is the shear modulus and this is the Poisson ratio.
But can it tackle large distortion density, where the distortion density is very high?
Look, all of these things will not work at very high dislocation density. The course, yeah. So there is a regime of validity for all of this. If the course starts to overlap, then these kind of things will fail.
So it assumes that there is no overlap.
Yeah, yeah. So all of this is somewhat low dislocation density approximation. Okay. Yeah, that was a very good point. Okay. So now, so which means that if I know the dislocation density, I can calculate stress. So this is the only message that you need to take from this slide. And now, if I know the plastic distortion field, I can easily calculate dislocation density. But the opposite calculation is slightly more difficult, but it's not that difficult because we know how to do it. I mean, we have done similar calculations in electrodynamics. So this is, if you know the dislocation density, can you calculate the plastic distortion field? And this is like saying, I'm sorry about the notations. J here means actual current density. So this equation is analogous to this equation. where this is Ampere's law without the displacement current. So J is equal to the curl of B. So if I know J, can I calculate B? And you can, and this is how you do it. So this is a similar expression, but in Fourier space. So this is a Fourier transform of an expression which is similar to this. Of course, we know that B is determined only up to some gauge transformation. And similarly here, there is some arbitrariness. If I know the dislocation density, beta is arbitrary. However, stresses and strains and displacements, there is no arbitrariness because that is decided by boundary conditions and so on. So that arbitrariness disappears, like exactly as in electrodynamics. When you work with vector potentials, there is some arbitrariness, but then you choose a gauge and then everything becomes okay.
You get estimates of the dislocation density from T?
Yes, but these models you will see is somewhat far away from directly taking from experiments. You will see the difficulty. I mean, this thing is not. It's modeling a real solid is not so easy, and you will see. Even a very simple solid is very difficult to do. But all that you can do here is to have qualitative understanding, and that there you can do really well. Okay, so once you know the plastic distortion field and the elastic distortion field, and then you can use mechanical equilibrium, etc., etc., and finally you can get the displacements in terms of the dislocation, Nye dislocation density tensor. So given the Nye dislocation density tensor, one can calculate all the other quantities and vice versa. So we have formally connecting the Nye dislocation density tensor, the plastic distortion field, and the stress. Okay, so this is, so far it is statics. Now dynamics. So the dynamics is done very simply. So we know that the dislocation density tensor is the curl of the plastic distortion field. Take time derivatives of both. So this thing is now the dislocation current density. I'm sorry I have used the same notation, but this is not the electrical current density, this is the dislocation current density, and that is given just by the time derivative of the plastic distortion field. Okay, so now we have to write down evolution equations. So first we will look at a system where dislocations don't interact. So in this case, the evolution equations are very simple. You are given a stress and you want to know how the dislocations move. So how the Nye dislocation density tensor, how does it change? Very simple. We will do the interacting case later on, but we have to do this. And the way these equations are derived is to demand that the total energy always decreases. So you see here that these theories are temperature equal to 0 theory. So it is the energy, the elastic energy, the total elastic energy always decreases as a function of the dynamics. Okay, we know that in finite temperature this is not always true, and the entropy comes in, and the free energy is the one which decreases, and the total energy may increase, dislocations may be created, and they can annihilate and so on. But here in the non-interacting as well as in the interacting case, we are going to assume that there are no thermal fluctuations which involve the entropy and the free energy. So it's just the total energy. You will get stuck in steady states. We'll come and we'll see that some of in some limits things become very intuitive. So, and you will understand this. So, in the no interactions case, the elastic degrees of freedom, let's say that they equilibrate much faster, because the time taken by elastic degrees of freedom to equilibrate would be of the order of the velocity of sound through the size of the system. Okay, so these things equilibrate much faster. So the only thing which is left are these plastic degrees of freedom, and you can show that basically stress into strain. So this is just showing that the rate of change of the total energy is the stress multiplied by the rate of change of the plastic distortion field. So this is the Jij. Okay, and I think the factor of half gets into, when you do the indices properly, it will come. So now one can show that the most general form. So what is the most general form for Jij, such that this is always decreases. So this has to be positive semi-definite. Okay, so this quantity, and one can show that the most general form is like this. If Jij has to be a function of the stress, then it has to be related to the stress linearly, and one can plug this in and prove that this always decreases. Okay, and here there is a fourth order tensor. So now once you have a form for this, given stress, you know this, and then you plug it here and you have the dislocation density as a function of time. Okay, so this is the evolution equation for the dislocation density, and it is very simple. Only thing is that you have to know this quantity, and for this quantity one can simply take the most general isotropic fourth order tensor. Okay, so isotropic nth order tensors, they will be, they can be written in terms of Kronecker deltas, and they will have some parameters in that, and these are listed in a book. So, and that book is on the internet, so you can simply go and search, I need the isotropic 12th order tensor. Okay, so the isotropic second order tensor is just the Kronecker delta itself, and then fourth order, and fourth order is this one. Okay, and I think up to 12th order is written, and things become very, very complicated and contains lots of parameters as the number of as the rank increases. Okay, so here there are two parameters, the CGL and CCL, and what these denote is the climb and the glide velocities. Okay, so you remember that climb was out of the plane and glide was in the plane. Okay, so of the so the dislocation, the dislocation tangent and the velocity, they define a plane. So if this thing, if the velocity is in that plane, so that would, no, the Burgers vector and the t, they define a plane. If the velocity is in that plane, then it is glide. If it is out of this plane, that would be climb. So one can show that this is nothing but the coefficients of climb and glide. So how much of climb and how much of glide? Okay. So so this is the most general form, and that is the evolution equation for the case with no interactions at all. However, if you don't have interactions, then nothing really happens. So you put a stress and dislocations move, so the whole thing distorts plastically, and if you remove the stress, it does not come back. That is all that happens. However, you cannot look at spontaneous formation of structures. spontaneous grain boundaries and cell structures. These you cannot address using the non-interacting model. As soon as you put in interactions, then you don't have only the external stress, but you have internal stress. And this internal stress depends on the density of dislocations elsewhere. So the density, if you have a dislocation somewhere, it produces stress, and then that stress acts on dislocations at some other place. Okay? So this is how dislocations will interact. And this is this interaction that we have to take into account. Okay.
Long-term thermal stresses.
Huh?
Is this what materials term as thermal stresses?
A thermal, yes. Long range stresses. Yeah. Okay. So, if a dislocation moves, the stress changes. The stress changes means that the force on some other dislocation at some other place will change. So that experiences this Peach-Kohler force, and then this dislocation moves. So a motion of a dislocation here will cause the motion of another dislocation there. So this is how things will get coupled. Okay. So the idea is whether one can write down a self-consistent equation. Okay. So stop me wherever I'm going too fast, because one has to do this in stages. So this is the Peach-Kohler force for a single dislocation, and that contains stress. Okay. The dislocation flux density of a single dislocation moving with some velocity can be given by a very simple relation. Okay, where the flux density is just the dislocation density multiplied by the velocity, and this delta function is just telling you that the dislocation is at a space point r equal to xi. Okay, so this is the most general expression that if you have a single dislocation. So now suppose I use a very simple ansatz that the velocity is simply proportional to the force. So it's some dissipative law. Velocity is equal to some mobility into some force. Okay. So then I will have to substitute for this velocity something which includes this force. Okay. So then this sigma comes here, and you can see that this is a second order thing. This fellow has two indices, and then this extra thing will have four indices, and the mobility tensor will have a 8 index quantity. Okay. So you can see how complicated this thing immediately becomes, and this 4 index quantity is just, this is exactly the coupling that we required. This is coupling a dislocation at one point with another dislocation at some other point. A dislocation is given by TIBJ. So you have two TIs, you have TIBJ and TKBM. So if you inspect, there are two T's and two B's. That automatically tells you that there are two dislocation density like quantities, and each dislocation density is a second rank tensor. So you have a fourth rank tensor here. So you have a fourth rank tensor, a second rank tensor, and an eighth rank tensor, all being contracted and giving you back a second rank tensor. So this is the most general expression. Okay, right? You can't solve this because you don't know this dislocation correlation function. Okay, so you have only dislocation density. So the dislocation density rate equation will involve the higher order correlations, dislocation correlations, and this is a very this we have seen in StatMech. that the equations of motion of some probability distribution, it always involves higher order probability distributions. And the only way to make progress here is to make a superposition approximation like this and say that the fourth order rho ij km is just rho ij rho km with some constant c which we don't know anything about. Okay, so now you'll see that how slowly and slowly we are putting in parameters which we don't know anything at all. Okay, so now we will do the same trick as before. Go to that book and find out the most general expression for the 8th order mobility tensor for an isotropic solid. Okay, so put that in, do all the algebra, and finally obtain the equation of motion for the plastic distortion field, which you will see that it involves stresses, okay, and the dislocation density elsewhere, which can be related to plastic distortion field again. So I have two equations now. One equation relates the plastic distortion field. Given the dislocation density, I can get the plastic distortion field and the stresses, and then the time derivative of the plastic distortion field itself. So this can in principle be solved self-consistently. The parameters which enter this are these mobilities. This number CD, which is a material constant, and this number lambda. So one can show that if lambda is equal to 0, then you are sort of treating climb and glide on the same footing. So it's completely isotropic. Okay, and if lambda is equal to 1, then there is no climb at all, there is only glide. In a real system, this lambda will be somewhere between 0 and 1. We don't know anything. So we don't know what is the value of lambda. We don't know what are the values of C's and D's. And we have made this approximation of an isotropic mobility. In a real solid, we need to find out all of these, and the isotropic approximation is not correct. Okay. So now, what is the use of this theory? You will see that even then, this is extremely useful because it allows one to understand structures that are obtained as a result of interacting dislocations. Okay. For example, if you have a low angle grain boundary, then one can derive a relation between the so a low angle grain boundary can be represented by an array of dislocations, okay, as in this picture. And you can derive a relation between the dislocation density and the angle between the two grain boundaries. And a little bit of inspection will tell you that the dislocation density is equal to 1 by the distance between dislocations, and that is just 1 by the Burgers vector into sine theta, which is just theta by the Burgers vector. And this is known as it's a simple example of the Frank condition, which can be written in complete generality as this. So given the angle difference, one can find out the dislocation density. Okay. So this is only for a symmetric tilt boundary, but for complicated boundaries it is much more difficult to derive in general, but it is possible. Okay. So now we are going to see whether arbitrary random distribution of dislocations can automatically by itself spontaneously arrange themselves into grain boundaries. And for this we will use these evolution equations. Okay. And we are going to write the evolution equations in terms of the betas because that is much more easy than the dislocation density itself. So to see that this happens, one can derive this entire thing in one dimension. So one dimension means that you have some kind of grain boundary here, and everything varies only in this direction. Okay? So I need to consider everything only as a function of z. Okay? So it is constant in y and x. So once you make this constraint, then you have to put in a lot of algebra, and I don't really have time to go through the full algebra, but one can write the evolution equation not in terms of the plastic distortion field, but one can directly write it in terms of the Peach-Kohler force, and then it takes a very simple form. So this is the evolution equation in terms of the Peach-Kohler force, and this equation is extremely well known in physics, and this is the so-called Burger's equation. Okay, so what does the Burger's equation do? Burger's equation says that if you take any field which is something, it has a smooth variation, then if you crank in time, then in finite time, such a smoothly varying field will produce shocks. Okay, so this will automatically produce sharp shocks at finite time. Okay, so what does it tell you? It tells you that the process of dislocations coming together and forming grain boundaries is nothing but the production of shocks. So a grain boundary which is just a concentration of lots and lots of dislocations in a tiny region is just a shock. Okay, so it's a shock front. So yeah.
That terminology is hidden in FPK.
Yes.
The form of
Yeah. So then once you have FPK, you can find out beta, you can find out dislocation density, and you will see that beta will have a step function like structure, but the dislocation density will have a delta function like structure. So dislocation density will be sharply peaked at a shock front.
But it is not that always these dislocations will form grain boundaries.
In this equation, in one dimension, it will be always. Yeah, you are right. But then these equations are not the entire story. So this is not our work. This is this work by Limkumnerd and Setna, and they show that they argue that the underlying physics responsible for these cell structures is just this. And you can do this in 2 dimensions also. Doing it in 3 dimensions will be quite difficult, but they have done it in 2 dimensions, and again in 2 dimensions you can form these shock-like things. But of course, to actually get these structures out, you have to make the mobility anisotropic and put in actual values of C's and D's, and no one has done that so far. So to compare with actual experiments, as you were suggesting, it is still very far. But people believe that the framework is there. Okay. So in the next few minutes, I'll tell you about, so far, I told you that this is about a material which is already plastic. So it already has some dislocations, and we are trying to find out what happens to those dislocations, either as a function of external stress or as a function of internal stresses because of other dislocations. Okay. But so this thing does not at all even address the question of how does a solid go from being an elastic to something which is plastic, okay, or how dislocations formed in the first place. So this question is unanswered up till now. So this question, as we will see, is quite difficult to answer, because you see that, you know, even the linear theory is so difficult, and production of dislocations will be something extremely nonlinear. So we don't expect the answer to be very straightforward, and there is a lot of controversy in this. So there are two kinds of situations where people look at. One is the situation which we already know from Laurent's lectures. Okay, so you have a stress-strain curve, and then at some point things become nonlinear, and then finally there is a stress jump, and things start to flow, and finally they break. Okay, so this is in the course of simple stress-strain experiment. But people also look at something called indentation, where you take a surface and you try to indent that surface using some hard, spherical, large, hard spherical particle, and you want to find out which are the regions inside this surface in the bulk where dislocations form. So this is from some computer simulations, and there is solid all underneath this surface, but they have not been shown. Only the locations of the dislocations are shown, and you can see that as you press this indenter harder and harder, dislocations suddenly form here. Okay, so these are the two situations that people usually look for. So if you have a homogeneous solid, the engineering criterion for yielding is the so-called von Mises criterion, and this is not really saying much. It is just taking the empirical yield stress in a pure shear experiment and trying to predict what is going to happen if you have an arbitrary shear. So what happens is that if you calculate this so-called distortion energy, then this distortion energy has some limiting value. Above that value, dislocations form, and the solid cannot distort anymore. So there is a limiting distortion, and beyond which you start getting flow. So this is a criterion which is based on some energy exceeding some threshold. So this is a global threshold criterion. Okay, and you can draw, make plots like this, and if you have a plot like this, and then you know the actual stresses, and you can see whether the stress falls here or there, and then you know that in such a situation whether my element is going to fail or not fail. And of course this is extremely useful to engineers who would like to design some bridge or a car or whatever. Okay, but in terms of physics, the content is very small, because you have not really explained anything. You have not said why things will yield when stress goes beyond this threshold. Okay, so that was the global yield criterion. You can also devise local yield criterion. So these local yield criterion will be useful for exactly the sort of situations that we had talked about, when you have an indenter. And this local yield criterion, this has to do with a local stability of the lattice. So you have the local elastic constants, and then you have the distortion field. So what is the displacement field at that point? Okay, and finally you can develop a criterion, and this criterion will be sort of based on if you have the phonon dispersion curves. These are inputs, and basically it looks at local phonon dispersion curves and finds out whether there are phonon modes which are unstable. So phonon modes are unstable when the omega of a phonon, the omega becomes imaginary. Okay? So if you have an imaginary phonon mode here, then things become unstable and the solid fails. So for example, this is the local phonon dispersion curve when you are sitting here in the stress strain curve, and this is the local phonon dispersion curve when you are sitting there. And you can see that here there is an unstable phonon branch. Okay, so you can use these kind of criterion to look at local yielding. However, this we'll see that there are one after another newer and newer work which sort of contradict earlier work. So both the global and the local yield criterion has to do with some threshold value exceeding a certain limit, and this threshold value is always some kind of stress threshold. So a Fourier component of a stress or some stress threshold, and here they find that it is more a stress gradient which causes nucleation of dislocations. So it is not the homogeneous stress at a point, but if you have a very large gradient, stress gradient, then dislocations form at such locations.
So that would be the case in the case for the indentation, but in the case of, let's say, uniform shear or
yeah, so there is no stress gradient, then this criterion probably can't be used. So there's a lot of different people saying different things. Yeah. So apparently this criterion gives you results which cannot be got from just stress threshold based criterion. Okay. And
What is the role of the crystal orientation?
the role of the crystal orientation is something that is very important, but here I think they ignored that. So it is taken in some specified orientation, and what they are saying is that I am going to look at the stress and find out the stress gradient. So here the stress gradient is highest, and this is where dislocations form, and that is exactly where they see that dislocations are forming. But on the other hand, the stresses are larger here and dislocations don't form there.
In all this,
Yeah.
the critically resolved shear stress,
Hmm.
you don't seem to have mentioned that at all.
The critically resolved shear stress comes when I was doing the von Mises criterion. So there that is the CRSS, yeah. I just didn't.
But in one of these,
Here it is implicitly there, because when they find out where it is going to fail, there of course it is going to fail in the weakest direction. So that is, of course it is there. I mean, yeah. So now we come to so all of this is not in the sense it is not a theory for yielding. So this is not a physical theory. You are giving a criterion, and these are extremely useful for designing materials, but this is it's not a physical theory. So the kind of physical theories which are used are things which which has already been discussed here. So I just tried to summarize this discrete element method, right? DEM, I think. Yeah. Huh? Yeah, but the essential model is very similar. So you have these connected n elastically connected elements. You put some shear, and then you look at the local shear there. If the local shear is larger than some threshold, then this element fails. Once this element fails, the shear is shared by the other connected elements, and then some of that can fail also. So it can create an avalanche. So if your shear stress is small, then no avalanche is created. But if your total shear stress is larger than something, then you suddenly have this transition, and there is this instability, and you start getting avalanches. You can measure avalanche distributions, and you can see that these are power laws, and then you can look at the universality class of these avalanches, and it turns out that these are of the so-called interface deepening class. I think, Lauren, today afternoon this will be discussed. But again, so this is actually determination of this universality class. But then again, you have papers like this, which says that yielding is not deepening. Yeah, so there's a controversy there. So whether this universality class is correct or not. So I'm just trying to tell you that there are, the jury is not out on this. And here the idea is that it is not deepening of dislocations, but unjamming. So dislocations were jammed, and at some stress, dislocations becomes unjammed. Okay, so there is some kind of a critical transition which happens at a certain high value of the stress.
But that again brings us back to this question of density of dislocations, etc. Right? So if this unjamming happens perhaps for large dislocation densities, whereas for small dislocation densities,
Except that if you have to put in a source, so as a function of stress, more dislocations may be produced. So then automatically there will be, yeah. Okay, but there are much more important problems than that. And this is something which sort of brings into question everything that I've told so far. And this is the problem of creep. So this problem is the following, that so long we have been assuming that I am pulling something for low stresses. This is elastic, and then at some high stress something is happening, and the solid fails. Okay, but this paradigm itself is questionable whether that is correct or not, and experiment says that it is not correct. And this is a sort of well-kept secret in the material science literature, because this is sort of antagonistic to whatever has been talked about before. And the experiment is very simple. You take a piece of material, maybe a metal, and then you put a stress on that. So as soon...
I think that what you say is not correct. It's a well-kept secret. What is important is the time scale. Here you are drawing a creep curve.
Everything will come out. Just wait and listen to me. Okay. So no, I'm saying that this is a little bit in jest. It is not, of course, a secret, because everyone knows about creep. So just listen to me. Okay. So here the experiment is the following, that you put in a stress. As soon as you put in a stress, there will be suddenly a strain. Okay, and this is going to happen at the speed of sound. So this is my elastic strain as a response to stress. However, don't remove the stress, and this stress is much below the yield stress. Okay, don't remove the stress, keep it. And watch the strain as a function of time. What we'll see is that the strain will not remain here, it will increase. And then it will be flat for a very long time. And then after some time, suddenly it will start increasing again, and it fails. Okay? And then suppose you increase the stress. If you increase the stress, this region becomes smaller. If you decrease the stress, this region becomes larger. But the nature of the curve more or less remains the same. Right? Yeah. And this axis is measured in log. So this can be days and weeks. So when I was doing metallurgy in my undergraduate, people told us that don't take up a project in creep because your PhD time will be determined by this time. Because if you are studying creep, then you have to, these experiments will go on for years, and you can't write anything unless the experiment is over. So this is a very long time. Now what? So it means that this failure, it occurs for any value of the stress. So only thing is that it takes longer. So any theory that you do should be able to describe this failure as well as the other one. You cannot have two different theories for the same phenomena in different time scales. Okay, you can, but you have to realize that then each of these theories will be approximate. So it will be nice to have a theory which can describe both. Okay, so this is, of course, now I will sort of end by going back to Greece. We started with Greece, we go back to Greece, and this is actually not Greece but Italy, and this is a fresco which is there in Florence, and this fresco shows two men, two philosophers. One philosopher is crying and the other is laughing, and these two philosophers are Heraclitus and Democritus. Okay, so Heraclitus, the guy who is weeping, he was known as the weeping philosopher, and he used to weep because he thought that everything is changing. So he made this statement, Panta rei, everything flows. Okay, so and for some reason that was very bad, it gave him a very bad vibe that somehow things are not steady, so everything flows. Democritus on the other hand made the statement that okay, things may flow, but finally there are atoms and atoms are indestructible. So what you are seeing as flow is just rearrangements of atoms. Everything what is happening is just atoms are getting rearranged. So this Democritus was a very interesting guy. I mean, he was an Epicurean. You can see that he was always laughing, and he was the son of a very rich person. He traveled the world, and people say that he had also come to India, and some of his ideas were already being discussed among the Jains, the Jain atomists and the Charvaka atomists in India. So these ideas were already there, Unfortunately, this fresco probably is completely untrue. This couldn't have happened because when this guy died, this person at most would have been a 10-year-old child. So they couldn't have sat together and shared wine and talked about this face to face. So the idea is that how it relates. I'm going to end here, more or less. I mean, how much time do I have? 5 more minutes. Okay. So this is this controversy that whether a solid flows or not. This is again. I'm not saying that it's a secret, but it is something that which should be pointed out more and more, because there are long review articles which show that actually there is no such thing as an yield stress, and the yield stress is strain rate dependent. So the lower the strain rate, the lower is the yield stress. It is a very smooth function. Okay. However, this variation is logarithmic, exactly the way Takahiro said, that if you decrease the strain rate by an order of magnitude, the yield stress changes by the second decimal place. So people can ignore it, but if you keep plotting how it decreases, it makes a extremely smooth plot, and the yield stress seems to go to 0 as the strain rate goes to 0. But when by strain rate going to 0, I mean strain rate going to 10 to the power minus 20, 10 to the power minus 50, and so on. So some really impossibly slow, at some extremely slow rate, the yield stress actually goes to 0. So we really have to understand this. And okay, so I just leave you with this following observation. And in the last class, we'll talk about some of the results that we have in our group, where I think we have an understanding of these two regimes within one framework. Okay, suppose, so this is really my last slide. So suppose you are given a solid like this, okay, and then you change the boundary, okay. So I change the boundary here. So this is pure shear. So then the crystal, these are the atoms, the crystal can do this, okay, follow the shape of the boundary. In this case, the shape of the boundary will be equal to some elastic strain, okay, and as a response to this strain, this crystal is going to produce stress, okay, and stress, half stress into strain is the energy. This is the rigid response. This is a solid which is a rigid solid, okay. However, the solid can do this also. There is nothing which prevents the solid from doing this, where it just nucleates a dislocation anti-dislocation pair which travel to the surface. Once it does that, you'll see that the boundary is respected, because I have changed the shape only with the boundary. So the boundary is respected, but inside the bulk there is no stress, there is no strain, and the energy is actually zero, okay. So in this case, the elastic strain is zero. So what this solid has done is to trade a bulk stress or a bulk energy to a surface energy. And if this solid was very large, then the surface to volume ratio would have gone to zero. So in the thermodynamic limit, the energy would not depend on the shape of the boundary. Okay, so in the thermodynamic limit, the rigid response does not exist, okay. So rigidity of a solid is always as a consequence of a metastable minimum. So you can get a rigid solid only if you somehow constrain your minimization, or if you look at a smaller time. As soon as you do an unconstrained minimization, you will always end up with a non-rigid solid. So concepts like yield strength will not exist if you have thermal fluctuations and if you are looking at a very large, solid in the thermodynamic limit at infinite times. Okay, so I'm going to talk about some models which explicitly show you how a constraint minimization will actually give you rigidity. So the first thing that I said, that rigidity is a consequence of broken symmetry. That is true only for a metastable minimum. That is not true globally. So this symmetry breaking gives you rigidity only when you restrict yourself to the local minimum, and not if you search out other minima. Okay? Of course. But after the defects have gone to the surface, there are no defects. So at the end of the process, there are no defects. So there is a large barrier between this and this. And because of this large barrier, producing this will take a lot of time. But we are not, we are not in a hurry. We can wait till the universe lasts. So in the thermodynamic limit, that is the main important thing. So how does this sort of become useful? And that is something that I'll tell you in the last lecture.
One thing.
Yeah.
No solid is perfect.
Yeah.
Every solid contains a certain density of defects. Even by when you pull a crystal. So any crystal, it is your dislocations which help the growth of the crystal. Okay? So I think starting with such an assumption that you have, perfect crystal is unrealistic.
No, but what is the question here? I am not asking the question about a real solid. I am asking a fundamental question, that given a perfect solid, is that perfect solid rigid or not? And I am saying that even a perfect solid is not rigid. Imperfect solids will of course not be rigid. I am saying, yeah. So no, this is a difference between a physics attitude and an engineering attitude. So here, the question is a physics question. That give me the most perfect solid that you can imagine, and I will argue and tell you that even such a solid will not be rigid. Okay, so this is the, of course, in reality, thermal fluctuations are going to create defects. So if a perfect solid is not rigid, then a solid containing defects will definitely not be rigid. Okay, so it's not the other way around.
Okay, I get your point.
The point is
I could see the profundity in what you are saying.
see what? The what?
Why you feel that it's a very profound statement that given a very rigid solid, it will still nucleate some dislocation?
No, the statement is profound in the sense that it shows that when you talk about a yield stress, you will always have to talk about yield stress at what strain rate. Okay, so the question of dynamics automatically comes. And then all of this finally would be completely useless if we can't calculate something. And at the end, we'll show that we can calculate the strain rate dependent yield stress, which will go from strain rates of 10 to the power minus 100 to 10 to the power minus 2. And we will show which kind of, we'll show that at small strain rates, it will be nucleation and growth, and at high strain rates, it will be spinodal decomposition like thing. So there will be spinodal criticality involved at high strain rates. At low strain rates, it will be nucleation, so which will be more like creep. And I will tell you exactly at what strain rate this transition will happen. So all of this will come. Physics asks always an idealized question, and from that idealized question, you will give an answer. So that is always the thing. And of course, each non-idealization will change the answer slightly, but the fundamental thing should be the same. Otherwise, there is no use.
So in thermodynamic theory, you
Yeah.
are saying the difference is actually zero.
In the thermodynamics.
So we know that from basic criteria,
Yeah.
that in the thermodynamic theory, the fracture strength is zero.
Yes.
But in the stress strain curve, that
Is always, yeah.
is the mean. It's
Yeah.
actually a point.
Yes, the stress strain curve makes sense only for a metastable solid. So, yeah, so this viewpoint, you may think that what is the point of this viewpoint? I know, and what does it give you? This viewpoint would be completely useless if it did not help us to calculate things. But now you will see that this will help us calculate things. That is in the last part.
Just one more point here. For the
Yeah.
heat, if you are taking a zero temperature solid,
Yeah.
then long time you will always get stuck if you are below the heating threshold.
In a zero temperature solid, you will never get nucleation and growth. So
Heat can happen for some time.
you will get stuck, of course, because you cannot cross the barrier. Yeah. Yeah, because you can't cross a barrier if you have.
The statement has been made that it's only a finite temperature effect where you have this.
I said thermodynamics. Thermodynamics means finite temperature. Thank you.